As I told you before, the finite element method is widely used to discretize differential equations because it does a very good approximation of the boundaries. Observe here how the boundary of the circle or the circular cylinder has very good approximation. Even it has a bump here, so it is correctly approximated also, and it uses elements that are not regular. It's not like a uniform sampling like in finite differences. Here the elements can have any shape, any number of sides, and even curved sides. Usually the elements are triangular or quadrilateral. They can have more sides, but these are the two most used most often. And the sides do not need to be straight, they can be parabolic. In this case, we need another degree of freedom at the middle of the side because a parabola needs three nodes to define the parabola, or it can be even cubic. In this case, with two nodes at the ends of the sides and two nodes at the middle, etc. And of course can be two-dimensional for two-dimensional problems, three-dimensional for three-dimensional problems. So these elements can adapt very well to the geometry of the object, but also to the variation of the fields. Here it is an example in which the field is stronger closer to the boundary of the object. Here maybe we'll change the color just in case it's more visible. Here the field is stronger when we are closer to the object surface, and for that reason the elements are smaller because the variation of the field is larger. There will be another slide about this later, but the idea of the finite elements is that in regions of the space where the functions to discretize have faster variation, the elements can be smaller, and in regions of the space where the functions have a slower variation, the elements can be larger. And very importantly, I will tell this again in the next slide, but very importantly, both the function inside, both the value of the function inside, value of f inside the element, and the boundary of the element, all of them are defined by polynomials using a systematic notation. In fact, we can consider the finite elements to be equivalent to basis functions. So conceptually, for us, these finite elements play the same role as the basis functions in method of moments. We expand the unknown as a linear combination of basis functions or finite elements. The only thing is the finite elements are formulated in a very systematic way using polynomials to interpolate the values of the function inside the finite element, so that the unknowns are the nodal values. The unknowns are the values of the function at the position of the nodes. Okay, for example, in this case, two different nodes have two different values of the function at these nodes, and these are the unknowns. And the values of the function inside the element here are interpolated from the values at the nodes using a systematic notation defined in local coordinates where the positions of the nodes are 0 or 1. You can there is a lot of literature and papers and books about that. You can find easily the notation if you look in the internet. But what is very interesting is that not only the function is interpolated using polynomials inside the elements, also the shape of the surface, that is the shape of the elements, is interpolated. In this case, it is a first order polynomial that is a straight line, but it could have been, for example, it could have been, if we define another node at the middle, it could have been a parabolic side, okay, as I told you before. Or it could be, for example, a cubic side. If we define two, can be, for example, cubic, if we define two inner nodes and we have overall 4 nodes for each side. Okay, so they are very flexible. In this case we have an example, and here we have an example of an object model with finite elements, and you can see how in the picture how accurately the finite elements can model the curved surface of the object. Clearly, this case is not electromagnetic. This is a case of structural analysis or stress analysis to simulate the deformation of the surface of the current due to some force. Because the finite element method is probably the method most widely used in engineering for numerical analysis or numerical simulations, although it is not the most common in electromagnetics. It is, if we count overall all the fields in engineering. It is very, very common. It is the method of choice in fluid dynamics, in structural analysis, thermal analysis, in many, many fields. When we have vector functions like the electric or the magnetic field, we have two options. We either discretize the three components of the field, x, for example, Ex, Ey, Ez, the three components of the electric field, using scalar finite elements like those here that just interpolate the value of the unknown. In this case, the unknown would be X component of the electric field, Y component of the electric field would be another unknown, and Z component of the electric field would be another unknown at the same node, 3 unknowns per node. Or instead, we can define vector finite elements that often impose some conditions on the components tangential or normal to the edge, conditions that are compatible with boundary conditions. In fact, these vector finite elements are generalization of the rooftop and Rowe-Wilton and Gleason basis functions that were introduced in the context of method of moments. In the case of Rowe-Wilton and Gleason basis functions, we had vector basis functions that have the property, they have the property that the vector field that you discretize is tangent to the boundary of the basis function and is normal to the inner edge of the basis functions. And these similar conditions exist for vector finite elements. In fact, vector finite elements are more general because they can discretize the unknowns with the polynomials of any degrees, and we can consider that method of moments rooftop and Rowe-Wilton and Gleason are just a particular case using first and zero order discretization of the unknown. But with finite elements we have more degrees of freedom, and using polynomials we can write a systematic formulation to have higher order finite elements. And how can we obtain the linear system using finite elements to discretize the differential equations? Well, in fact, there are two ways to formulate the finite element method. One is based on weighted residuals. In fact, imagine that you are doing a conventional method of moments discretization, but your basis functions are the polynomial finite elements. So instead of let's say rectangular or triangular method of moments basis functions, you just use your finite elements that are defined they are defined as polynomial functions in a normalized space where the position of the nodes is 0 or 1, and then you do a transformation to the real space, etc., etc. But you, using these finite elements, you use these finite elements as basis functions. And then your linear operator is the wave equation, and you use, here you just set up the conventional method of moment discretization, and very often you use point matching, that is weighting functions that are delta functions, so that your weighting is just taking samples of the residual and making this residual at the position of the samples equal to 0. So in this case, there is nothing new for you. You already know method of moments, so you just take the finite elements as the method of moments basis functions, use point matching, that is delta testing functions, or just sampling the residual and setting it to 0 the position of the samples, and you get the linear system matrix. But now the linear operator is a differential equation, and as a result you will get a sparse linear system. You will get a sparse linear system similar, very similar to the linear system of the finite differences, but with other coefficients, because now the unknown has been approximated not with a regular grid, but with these finite elements that can be as close as the boundary as we want if we increase the degree of the polynomials that approximate the boundary. There is a second way to formulate the finite element method, and it's called the variational formulation. In this case, we define a functional of the unknown. That is, if the unknown is phi, which can be the potential or the field, imagine for example that phi is the potential, we define a functional that has the property that it has a minimum. So this is the functional of the unknown. It has a minimum. Here we have the unknown. Of course, the unknown, this is an infinite dimensional space. I just make the drawing in one dimension for clarity, but it is infinite dimensional. The functional of the unknown has a minimum where the unknown is the solution of the problem. For example, imagine that this functional is the stored energy in an electromagnetic problem. You know that the stored energy must be minimum, so at the minimum of the stored energy function, the potential is exactly the solution of our problem, is the potential that really would exist in this structure, because it must be the potential that produces the minimum energy. Okay, so the way to get the linear system of equations is just to derivate the functional with respect to the unknown and setting the derivative equal to 0, because then we can isolate the values of the unknown phi that make the functional minimum and are therefore the solution. To do this, we discretize the unknown as a linear combination of the finite elements. These are the finite elements, or in the basis functions in the context of method of moments, and then our unknowns become the coefficients of the linear combination. That I told you before that in finite elements, the unknowns of the vector of unknowns are the values of the function at the nodes. So here the unknown coefficients, again, here the values of the coefficients would be the unknown evaluated at the position of the nodes. Okay, the sample of the unknown at the nodes. And now we have to compute the derivative of the functional with respect to the unknown. The unknown is discretized as a vector of unknown coefficients. So we derivate the functional with respect to the coefficients. Of course, the functional is now a function of the coefficients because we have expanded the unknown as a linear combination of the finite elements multiplied by the coefficients. So the functional is a function of the coefficients. We derivate it with respect to the coefficients and set the derivative equal to 0. Here we have since the finite elements have polynomial expressions, we can easily derive the matrix that multiplied by the coefficients gives independent vector. This can be the matrix, let's say A, for example, whatever. The independent vector, as always, comes from the boundary conditions, where it's here. Here, adding the boundary conditions, we obtain the independent vector because remember, the same as we did in finite differences, we set the values of the unknown at some nodes equal to the known value given by the boundary conditions, and these values are no longer an unknown and go to the right hand side at the independent term. So the independent term comes from setting the boundary conditions at some values of the unknown function. And in this way we obtain a linear system that often can be the same linear system as we obtain with weighted residuals. And it is also very interesting that in finite element methods we can adapt the size of the mesh to the variation of the function. I introduced this before, but clearly, for example, imagine that this is the potential or whatever. We have some source. Imagine, for example, that here we have an antenna, so the field is stronger close to the antenna, so it has a faster variation close to the antenna, okay, and much slower variation away from the antenna. In this case, we can use smaller elements near the antenna for more accurate discretization. And finite element methods allows you to do this automatically. There are formulations of finite elements that identify the elements where the variation of the function is larger, and then they divide these elements into smaller ones, and then you can do this recursively several times, and at the end you get a very fine mesh where you really need it, and larger elements where you don't really need that much variation, and it's very convenient in many fields of engineering. In the case of electromagnetic waves, you are limited to the fact that if you have a wave propagating, you have a phase so that the real and imaginary parts are sinusoidal due to the phase, and you have to sample, usually you need about 10 samples per lambda, per wavelength, and this makes this limits the maximum size of the elements. The maximum size of the elements in the case of electromagnetic waves must be smaller than lambda over 10 or lambda over 20 for finite for methods based on differential equations. So what you can do in electromagnetic cases is to do a very fine sampling where you know that there is a very fast variation of the magnitude of the field. But however, you cannot use very large elements like this if they are larger than lambda over 10, because then you would have an undersampling of the phase, although the smooth variation of the magnitude would be correctly sampled. So for example, in fields, in other engineering fields, structural dynamics, you can have very large elements in areas where for example, the stress of the structure is almost constant, and very small elements where there is a very fast variation. In electromagnetic waves, you are limited to the fact that the maximum size of the elements must be usually smaller than lambda over 10 or lambda over 20. Well, an important issue is that, of course, the finite element method, since it is a differential equation method that needs a volume discretization, it needs a truncation boundary condition the same as the finite difference method. So you can either use the Moore's absorbing boundary condition, the perfectly matched layer, or whatever, but there is another option that is used sometimes, that is just to set an integral equation at the boundary, and then the integral equation at the boundary obtains a relation between the values of the unknowns and the boundary, and you can use this integral equation as your truncation boundary condition. In this case, since the integral equation has a convolution, it relates all the nodes at the boundary with all of them. That is, there are coefficients relating all the nodes at the boundary with each other. So you get a submatrix, you get a completely full submatrix that relates the nodes at the boundary. That is, if we have here the unknowns vector, the rows corresponding to this full square at the boundary, this is the rows that correspond to the boundary. Okay, so, or here, better here, this corresponds to the boundary samples, and here you set the boundary condition at the boundary. Okay, so this submatrix is the method of Mammond's discretization of the boundary, where you have an integral equation, and the rest is the finite element discretization of the samples at the nodes of the finite element. So it is a hybrid finite element discretization inside your inhomogeneous object, and integral equation or boundary discretization in the boundary. In the context of finite elements, this integral equation, this surface integral equation at the boundary, is called boundary element method, BEM, which is boundary element method, or boundary integral finite element method. Okay? And as I told you before, the finite element method is really the most commonly used method for numerical simulation in many areas of engineering, and not only engineering, but also chemistry, physics, etc. But in engineering, you have solid mechanics, structural mechanics, fluid dynamics, heat transfers, acoustic, also electromagnetic waves. But in the context of electromagnetic waves, probably the finite difference time domain method and the integral equations discretized by method of moments are more used than a finite element method. It was developed in the 60s, and in fact at our university at UPC we have the Center for Numerical Methods in Engineering, which is one of the best centers in the world dedicated to finite element methods in different topics in engineering. And as I told you before, the nice thing of finite element method is that it has a systematic formulation, so it is easy to formulate and to program, and the flexibility of finite elements to model the geometry makes it very good to model complex inhomogeneous structures like this in the pictures. Okay, but I told you before, in finite element methods, as in all methods based on differential equation, you need a mesh truncation condition that can be a perfectly matched layer, can be an older absorbing boundary condition, or can be, as I told you here, a integral equation defined on the boundary. And we will finish differential equation methods with a third option, the finite differences in time domain method, that is also a method that is widely used because since it is in time domain, remember that methods in time domain are very good for a wideband analysis of the of whatever parameter we want to compute. For example, imagine that you want to get the, let's say, the reflection coefficient of an antenna as a function of frequency. Okay, if you use a frequency domain method, you must repeat the calculation at many frequency samples, many times, maybe 100 frequencies, and this is very time consuming. However, if you solve it in time domain, it may cost more. It can be more expensive than obtaining the frequency solution for a single frequency, the frequency domain solution for a single frequency, but on the other hand, after a Fourier transform, you get the solution for the whole frequency band. So time methods in time domain are also important, are also widely used in electromagnetics, and finite differences in time domain is probably the first and the most important, although they are variations with better approximation of the geometry, but conceptually it is the most important. It is a discretization of directly the Maxwell's equations, not the wave equation, directly the Maxwell's equation. To show you an example, we define a one-dimensional problem. In one-dimensional problem, we have a wave that propagates along the z-axis, okay? So we have an electric field in x direction and a magnetic field in y direction that are transverse to the direction of propagation z, like this, okay? And then substituting this wave in Maxwell's equation, with the curl of electric and magnetic field becomes a derivative with respect to z coordinate, and the Maxwell's equations become very simple, just a small system of two differential equations that we can easily discretize. To discretize them using central difference, remember I told you that it's important to use central differences because they give the best approximation of the derivative. We sample the electric field at the z-axis at k points k, and in time at points n. Okay, so for clarity, we will use a short notation in which k is a subindex denoting the position in space. The sample is at set k, and the superindex n denotes the position in time. You sample at time tn. Okay, so the idea is that the subindex is the position in space and the superindex is the position in time. So here space and time, okay? Well, we have the derivative of the electric field with respect to z coordinate, and this means that using central differences we have to subtract a sample at the right minus a sample at the left. So we subtract a sample at point in space k plus 1 minus sample at point k, and what we get is the derivative at the center of k plus 1 and k. So get the derivative at position k plus 1/2. So the magnetic field is obtained at position k plus 1/2. So here we can observe that in space the magnetic field is at position k plus 1/2 because it is the middle point between the two samples that we subtract to compute the derivative k plus 1 and k. Now we must also discretize the time derivative. Let's change the color for the time derivative, blue color. so time will be blue color. In blue color we have the time derivatives of h, but we have to compute the time derivative of h at tn. So using a central difference scheme, we must subtract the sample at n plus 1/2 minus the sample at n minus 1/2. So we get the sample at tn. Okay? So this is very important because this means that the samples of the electric field and the magnetic field are interleaved both in time and in space. Both in time and in space, we have an interleaving between the samples of electric field and the samples of magnetic field. The samples of magnetic field are at the middle points of the samples of electric field, both in space and time, and vice versa. The same happens for the electric field samples are at the midpoint between the samples of the magnetic field, both in space and time. We do the same kind of discretization for the other equation, and here we subtract samples in Z to obtain the derivative of the magnetic field with respect to Z coordinate. So we subtract the sample at k plus 1/2 minus the sample at k minus 1/2 and obtain the electric field and the current at position k. Okay? And in time, here, in time we subtract, then we have the time derivative of the electric field, so we subtract the electric field at position time plus 1 minus n, and we subtract the sample at n plus 1 minus the sample at n, and we get the derivative of the electric field, which is the magnetic field, at position n plus 1/2, that is the midpoint between n plus 1 and n. Okay, so now we have a coherent discretization. Using this trick of samples at the middle point, we have now a discretization of the Maxwell's equation in which everywhere we have used a central difference that is the most accurate option. So we just copy this equation to the next slide and get this. This is what we copied from the previous slide. And now we have to solve this iteratively. We can solve this iteratively without setting a system of equations. What we do is to isolate, in each equation, we isolate the samples at a later time. In the first equation, the sample at a later time is the magnetic field at time n plus 1/2, because all the other terms correspond to samples at time n or time n to minus 1. So we isolate this term here, and we get this equation, which is just the same equation isolating the magnetic field at time n plus 1/2. We do the same thing for the second equation. In the second equation, the latest term is the electric field at time n plus 1. All the other terms at a time n plus 1/2 or n. So we isolate this electric field at the latest time n plus 1 and get this equation, which is just the second equation with a isolated electric field at the latest time. And in these equations, we observe that we can recursively compute the fields. If we know the fields at time n and earlier, we know the fields at time n and earlier. So we know, let's just delete this. Okay, we know the fields at time n and earlier. So we know the fields at time n, we know the fields at time n minus 1/2, and we can compute the magnetic field at time n plus 1/2. Then we use this magnetic field here at time n plus 1/2, and we also use the excitation. The excitation is a function of time that is known for all at all time samples. So this is known. This is the excitation. Then we also know that the electric field at time n, because I started saying that we know the solution at time n and earlier, and therefore we can compute the electric field at time n plus 1. So observe that having both the electric field and the magnetic field at time n and earlier, we can compute the magnetic field at time n plus 1/2 and then the electric field at time n plus 1, and do this recursively after setting n equal to n plus 1 in our algorithm. We do this recursively and then we go back to the start and again compute a magnetic field at n plus 1/2 because n has been updated to the next time step, and the electric field at n plus 1. Then we again update n equal to n plus 1, etc. And it is very easy to program because if we just copy, I just copy this equation to the next slide. I just copy this to the next slide. Here, this is what I copied. Okay. And this is very, very easy to program. This is just the Matlab loop to implement these equations. It's so easy. One of the interesting papers that I uploaded to Atenea Digital Campus is a paper on programming the one-dimensional Maxwell's equations in Matlab using finite difference time domain. In fact, it is essentially this loop, but there is much more stuff because there are a lot of things to take into account. But anyway, it's so simple, and if you want to program it, it's up to you. It's not it's by no means a mandatory exercise. It's just something you can do if you wish. It's very easy and very simple to program. In fact, you will do later an assignment in which I have programmed all the methods for you to solve the one-dimensional wave equation, and one of the methods is finite difference time domain, and you will see this loop program there. There are many issues to take into account, and the most important one is the time step. The time, you know that the sampling in space must be much smaller than the wavelength to correctly sample the phase of the waves, and often we use steps smaller than lambda over 10 for integral equation methods and often smaller than lambda over 20 for differential equation methods. But we also need to set a condition for the time sampling. The time step must be smaller than the space step divided by the velocity of propagation. That is, we have to sample in time no later than the time the wave takes to reach the next sample in z coordinate. So just if the speed of propagation is c, the time that the wave takes to reach the next sample is delta z over the speed of propagation, and our sampling in time must be smaller than that. Very often we choose just the equal condition because this is enough. There is no need to sample at a smaller time step. This is enough and it works. So the less samples in time, the faster the computation. But in practice, the problems that we have are two-dimensional or three-dimensional, because one-dimensional problems are only pedagogic to learn the method, but in real problems are in 2D or 3D. So in 2D we have to discretize the Maxwell's equations, and we get this for T. Of course we have to distinguish between TE and TM cases, but for the TE case we have these equations, and now we also have our discretization has also an interleaving between the samples of the electric and the magnetic field, so If this is magnetic field, electric field, this would be magnetic field, this would be electric field, etc. And the same here, magnetic field, electric field, etc. There is that interleaving, the same as in 1D, but extrapolated to 2D. But now we have different components of the electric and the magnetic field, and we have to interleave them accordingly. You can find all this in the literature, but again, the stability condition, I didn't tell you, but this condition was called current stability condition, the condition for the time sample. The current stability condition now becomes similar, but using both the diagonal of the square and the discretization. This is delta x, delta y. So you have to set the stability condition using the diagonal of the square. And in 3D you have a similar thing. You discretize the equations. Now you have the three components of the two fields of electric and magnetic field. They have three components, and the interleaved discretization of the electric and magnetic field is a real mess. But G was able to develop this formulation in the late 60s, maybe 68 or 69, something like that, or 66 maybe, I don't remember, but in the 60s G developed this formulation, and it's much more complex than, of course, the one-dimensional very simple formulation, but it's not that difficult and anybody can program it. The equations to program are in the literature, and in fact it is easy or less difficult to program that than other computational methods. The condition now is for the diagonal of the cube. So here we have our cube, and we have to compute the stability condition for the diagonal, that is delta x square plus delta y square plus delta z square and the square root of the sum. Okay, the diagonal gives us the stability condition. The diagonal over the speed of propagation gives us the maximum time step. This method, this finite difference time domain, or FDTD, has a number of advantages that made it, and it's one of the methods mostly used by commercial software. In fact, it's applicable to highly inhomogeneous and complex media, because you can the only thing that you need is to have a sampling. You have to set cubes like this, but you can easily make a volumetric mesh for a highly inhomogeneous medium with a very large number of unknowns. In fact, the important issue is that if the medium is highly inhomogeneous, it needs a very large number of samples to accurately model the geometry. And if the number of samples is very large, millions, thousands of millions, you don't want to solve a linear system, because remember that with finite with differential equation methods, you don't have a fast solver. You have the possibility of using sparse matrix solvers, but you don't have a fast solver like MLFMA. So normally it is, if the number of unknowns is so high, it's better to use an iterative method like this that doesn't need to set a linear system and to solve a linear system. So since it is applicable to very large number of unknowns with low memory and no matrix storage, no linear system to solve, it is very good for inhomogeneous media, because they need very large number of unknowns. And also, very importantly, it is very easy to implement in large scale with large scale parallelization in supercomputers. The way the equation has no convolution, so the samples are related only to the neighbors, and it is very easy to distribute the task of this loop in three dimensions is much more complicated because you have to use this discretization scheme. But anyway, the resulting algorithm is easy to parallelize in supercomputers because the different nodes, you can use a supercomputer having thousands of nodes, and the different nodes analyze different parts of the problem with a small amount of communication between nodes. So it's very good for programming in supercomputers. So you can solve extremely large problems using this method. Of course, it's a solution in time domain that is very good if your excitation is non-harmonic. If your excitation is a pulse, obviously it's the best method because you get directly the time domain solution. But also, if your excitation is harmonic, but you want a wideband solution, remember the example that I said before about computing the input reflection coefficient in a frequency band, and you want a lot of samples, a lot of frequency samples, instead of solving the frequency domain problem at many frequencies, it is much better to solve the problem in time using FDTD as a function of time, and then using using a Fourier transform of the problem in time, you get your parameter, your solution. Sorry, this is not F. This is wrong, and this is wrong. I meant this. You solve the reflection coefficient in time, and you do a Fourier transform and get the reflection coefficient as a function of frequency. Okay, so it's very, very good for wideband solutions. Well, and just some comments about the problems and difficulties in finite difference time domain. I have already talked about some of them in the previous slides. For example, about the mesh truncation condition. Of course, you have to truncate the mesh. It is a finite method, a method based on discretizing these differential equations. So you need the mesh truncation condition. But if you have to program it yourself, you will use a very simple and easy absorbing boundary condition. If you use commercial software we use a perfectly, let's change the color, for example, this, we'll use a perfectly matched layer that will absorb the waves. But anyway, you need it, an easy one or a complex one, but anyway, you need some mesh truncation condition, the same as in finite difference frequency domain or in finite element method. Also, I told you about the current stability condition that limits the maximum time step. This means that if we need to sample on a long frequency interval, because, for example, if we need a response in a high frequency range, we need if we need a very fine sampling in frequency, for the Fourier transform we need a very long domain time interval, and a very long time interval. If the time step is small, we need many time steps. That makes the computation longer and less stable, because instabilities may arise when we are computing the iteration at very long times. Also, the grid is uniform using the G discretization scheme that I explained of interleaved electric and magnetic fields. We have uniform samples. They are interleaved. Okay, but anyway, we need uniform samples. So the boundary has this staircase approximation. For example, for that circular cylinder, there is a staircase approximation. I talk about this issue in finite difference method. Here it is the same thing in time domain, the same problem. This means that for accurate modeling of the object, we need a very small space sampling, and a small space sampling means also a small time step, because they are related. The time step is limited by the space step over the velocity or speed of propagation. Okay, and this will increase a lot the computation time. For that reason, the modern methods use non-uniform grids or conformal grids. They are similar to finite element method in using non-uniform cells, so they use cells like that are non-uniform, but the procedure is still sorry, we were here. Yes, the procedure is still in time domain and iterative, so it is a kind, let's say, of non-uniform finite difference time domain method. There are a lot of names for this, but you just can imagine this finite difference time domain using a non-regular grid and with cells that can adapt very well to the geometry. These are the modern implementations that you find in commercial software. But there is another issue. It's called numerical dispersion. The problem is that the phase velocity is equal to the phase velocity in the numerical grid, that is the numerical phase velocity, is equal to the phase velocity of the wave in free space only for very small space steps. The reason is very simple. If we have a wave originating at a source here, using finite difference time domain, we compute the field at the neighbor points, and then at the next time step we again compute it at the neighbor points, okay, and then again at the neighbor points. So our wavefront is not spherical. Our wavefront is not spherical. That means that the speed of propagation depends on the direction of propagation, which is mesh anisotropy, and not only on the direction of propagation, but also is only accurately equal to c if the space steps are very small. In one dimension, we can also have a speed of propagation equal to c, that is no so no numerical dispersion, if the time step is equal to the maximum given by current stability condition. So it is very good to use this because in one dimension this removes the numerical dispersion, but if we use smaller time steps we will get a numerical dispersion. You can see it in the programs that I have written for you to just run the programs as an assignment. You will see this. Okay, and in 2D and 3D, as I said before, the phase velocity depends on the direction of propagation. I can just show you this issue here. The idea is that we need a very small space sampling, a very fine sampling, and we can see here how this is the group velocity of the wave normalized by the group velocity in free space that would be equal to c. Okay, so only for very fine sampling, this is the number of grid cells per wavelength. So for very fine samplings of let's say 40 cells per wavelength, that is a sampling step smaller than lambda over 40, we get a phase velocity, numerical group velocity equal to the velocity corresponding to free space. Okay? However, we can use lambda over 20 instead of lambda over 40, that is 20 grid cells per wavelength. With this, the results are not so bad. We almost get, this is 0.99, so we almost get the same speed of propagation as in free space. It's not bad. If we need to use a coarser sampling, we need less samples to reduce the computational cost, we can survive with 10 samples per wavelength, that is sampling lambda over 10. This is not very good, but well, it's the minimum we can use, but less than that we shouldn't use. Lambda over 20 in finite difference time domain, lambda over 20 is commonly the choice of the best choice, because it's a good compromise between accuracy and computational cost. And regarding the mesh anisotropy, I show you here the propagation of a cylindrical wave. It's a two-dimensional problem, a cylindrical wave, and you can see that with very fine sampling, the wavefront is almost completely cylindrical, so it works very well. If we reduce the number of samples to 25, it is still okay. We can see here some very small defects, but it is still almost cylindrical, so 25 or 20 cells over per lambda is okay. This is a sampling about lambda over 20 that I told you is normally the best option. If you use 10 cells per lambda, you can see here that the wavefront is not completely cylindrical. There are defects in clearly there is some error. This is the minimum, absolute minimum that you should use, because if you shoot less than that, if you use only 5 cells per lambda, the results are completely wrong, because the speed of propagation depends so much on the direction of propagation that the wavefront is completely different than a cylindrical wavefront. As you can see here, that the speed of the velocity of propagation is completely different than C. Okay? Here there is another example in which I show you the normalized phase velocity or group velocity compared to C for different sampling rates, and we see that for 20 points per lambda, it is almost equal to 1, which is the conclusion that we got. So sampling lambda over 20 is very often the best choice. There are many applications of this method. I told you that it is very good for highly inhomogeneous objects, like for example, imagine this printed circuit. This is an example that you can find in the wave of this commercial software. Also for wideband simulations, and as examples of very complex inhomogeneous objects, here you have a model, a very detailed model of a human head, a complete model of a human body for electromagnetic resonance, etc. There are many applications, and normally it's the method of choice when the geometry that you want to model is extremely complex, and you also want a wideband simulation. And we will finish this chapter dedicated to numerical methods with some commercial software examples. Of course, this is not a complete list. These are just the examples that came to my mind, and probably the most commonly used software is here, but of course there may be other important software packages that are missing. But however, this is just what I can, the ones that came to my mind, maybe because we use them at our laboratory or because I know them better than others. Okay, FECO. FECO is one of the most widely used software packages for electromagnetic analysis. Originally it was based on integral equation method of moments, but now it includes all methods. The other software that is very commonly used and very widely used in computational electromagnetics for numerical simulation is CST. CST originally was a finite difference software it was a kind of non-uniform FDTD, but now it has all the methods and multiphysics. So the most important software packages, modern software packages, has now all the methods like FECO, like CST. Another interesting software package is Momentum. Momentum is embedded in the ADS circuit analysis package that you have used in your laboratories at the Telecom school. Also CST, if you are following courses on antennas at the Telecom school or here at the master, you have used CST. Momentum is interesting because it is special for the multilayer media greens function, so it is for printed antennas and printed circuits with multiple layers. So the idea is that instead of using the integral equation in free space, it uses the Green's function. It is an integral equation analysis discretized by method of moments, but instead of using the Green's function of free space, it uses the Green's function for a infinite multilayer media. So it is very good for printed antennas and circuits, and probably the best choice if you want to analyze one of these. It is integrated in ADS package. Nufasan is another software based on integral equations. It is interesting because it is developed by a Spanish group, so for us it has some interest. It is based on integral equation with method of moments, but it also includes a high frequency approximation that are the topic of chapter 4. And the main difference between this software and the others is that this software introduces the modeling of surfaces for integral equation analysis with method of moments. It introduces models with curved surfaces. These NURB surfaces mean non-uniform rational B-splines, that are surfaces that are parametric surfaces that are in fact curved, and it is able to define basis functions in these curved surfaces and solve the surface integral equations with method of moments with a very accurate modeling of the geometry. This is probably the best differential feature between this software and the others. Anyway, it's very good and developed by a Spanish group, and I like it a lot. Now, regarding finite element method software for electromagnetic analysis, you will find lots of finite element method software packages for analysis in different fields of engineering, but for electromagnetic problems, HFSS is probably the most widely used and a very good one. For finite element method, there is also other software package that is interesting to us, is COMSOL. It is a multiphysics simulation software that of course has electromagnetic modeling. It uses finite element method, but the nice thing of this software is that it includes multiphysics, so you can integrate many models, electromagnetic simulation integrated with heat transfer, maybe with a structural and deformation, structure deformation if the piece is moving, whatever. It can do a multiphysics simulation, which is also a very interesting feature. Regarding FDTD method, again, the CST software package is a very interesting one. It was mentioned in the context of integral equations, but I told you that it was originally developed as a finite difference in time domain software, and now it has all the methods, and even it has also multiphysics simulation. And they use a technique to model the structure using non-uniform cells that they call finite integration technique in time domain, but it is a kind of FDTD for non-uniform cells. Another interesting software is Empire. Again, they also have non-uniform mesh. I told you that all modern software packages, important software packages for FDTD use non-uniform meshes. They call it local conformal mesh for curved geometry, but anyway, there are different ways of formulating the solution for a non-uniform mesh. It is interesting because they claim that it has very high computational efficiency. And finally, another FDTD software that is also interesting because although it is electromagnetic, it is developed for optics. So it is electromagnetic but at the light frequencies. And therefore it includes lots of effects, of optical effects that must be taken into account, for example, the plasmonics, modeling nanoparticles, etc., liquid crystals, many options for analysis of optical problems. So I just gave you a very short list of software packages, but I told you it's not a complete list at all. There are many others. These are just the software packages that are either used at my department, or I know them for some reason, or I like them, or whatever. But there are many others, and you can search in the internet for different software packages. So with this we finish sorry, the chapter on numerical methods, and the next chapter will be dedicated to scattering and high frequency approximations.